There are situations the limit will give you indeterminate form of 0 over 0 when you use direct substitutions. In those cases, you may want to find another approach to find the existence of limits. When that is the case, you can use something called the two-path test for non-existence of limits. That is, if f of xy approaches two different values as xy approaches the point AB along two different paths in the domain of f, then the limit of the function f of xy as xy approaches AB does not exist. For example, if you consider the following limit, so you have the limit of negative xy over x squared plus y squared as xy approaches 0, 0. In example 3, you can see that the limit of this function as xy approaches 2, 1 is very easy to find the limit by using direct substitutions. However, in this case, the domain of the function is everything except the origins. Therefore, when you apply direct substitution for this limit, you will get the indeterminate form of 0 over 0. So that is by direct substitution. You get that the limit of the function is equal to 0 over 0, which is again the indeterminate form. Now we're going to apply the two-path test for non-existence of limits. So the procedure for this type of limit is that you find the limit along the path x equal to 0, so that is the y-axis, and then you find the limit along the path y equal to 0, that is the x-axis. If the limit along these two paths equal to one another, then you move on to the third path, which is the limit along path y equal to x. And if the limit of these three paths equal to one another, then you continue moving on to another path. So for this example, I'm going to consider in finding the limit along path x equal to 0, finding the limit along path y equal to 0, and find the limit along path y equal to x. So that is find the limit along path x equal to 0. If this is the case, then y is fixed. So that is, you have the limit of the function negative xy over x squared plus y squared of x comma y approaches the point 0 comma y. Here you can use direct substitutions and you get negative 0 times y divided by 0 squared plus y squared, and you get the limit to be equal to 0. Now you do the same calculations in finding the limit, but along the path y equal to 0. So find the limit along path y equal to 0. In this case, x is fixed. So the limit of the functions negative xy over x squared plus y squared as x comma y approaches the point x comma 0. You get, again, to calculate this limit, you can use direct substitutions and you get negative x times 0 over x squared plus 0 squared. So this is 0. So in finding the limit along these two paths, the result is the same, which is the limit is equal to 0. So it's not going to tell you much about the limit. So remember, the limit is going to exist along all the paths. This kind of question is asked. Usually the question is going to point you to the results that the limit does not exist. So you may want to consider as many paths that you can think of, so that you can find out that the limit does not exist in this kind of problem. So I'm going to move on to the third path, that is find the limit along path y equal to x. So that is, you want to calculate the limit of the function negative xy over x squared plus y squared for x comma y approaches x comma x, because y is equal to x in this case. So by direct substitution, you get negative x times x, because y equal to x in this case, over x squared plus x squared. So if you do the calculation, you're going to get the results to be negative 1/2. So since the limit along path y equal to x is different from those along x equal to 0 and y equal to 0, you can conclude that the limit does not exist. So since the limit along y equal to x is different from those along x equal to 0 and y equal to 0, you can say that the limit does not exist. So that is the procedure of defining if the limit of the function exists or not. So the reason for this approach or this procedure is that when you use direct substitutions to calculate the limit of the function, you have the indeterminate form. And usually when you ask this kind of questions, the limit may not exist at all. And therefore you may want to find the limit along two different paths, and hopefully the result of the limit from two different paths will be different from one another. So therefore you can conclude that the limit does not exist. Now we're going to do a similar problem in finding the limit or determine the limit of the function exists or not. So you want to find the limit of the function x squared minus y squared over x squared plus y squared altogether square. So if you consider this functions, the domain of the function is everything except the origins again. So therefore, when you do direct substitutions, you will see that the limit of the function will be 0 over 0, which is the indeterminate form. So by direct substitutions, you get that the limit of the function f of xy, given that f of xy is equal to this function. As x comma y approaches 0, 0, going to give you 0 over 0. And again, this is indeterminate form. When you see an indeterminate form, you want to find the limit along different paths. Similar to the last example, you want to find the limit along path x equal to 0, find the limit along path y equal to 0, and find the limit along path y equal to x. So first, you want to find the limit along path x equal to 0. So in this case, y is fixed. So that is, you want to find the limit of the functions f of x comma y as x comma y approaches 0 comma y. Again, the functions f of xy is x squared minus y squared over x squared plus y squared altogether square. So I don't want to keep writing the functions over and over again. So I'm just going to let the functions here to be f of x comma y. By direct substitutions, x in this case is equal to 0, y is still y, so you get 0 squared minus y squared over 0 squared plus y squared altogether square. So you get negative y squared over y squared square. So the result is going to be positive 1. Now we're going to find the limit of the function along path y equal to 0. In this case, x is fixed. So find the limit along the path y equal to 0. So that is x is fixed. So you want to find the limit of the function f of xy as x comma y approaches x comma 0. So you get x squared minus 0 squared over x squared plus 0 squared altogether square. Again, I get this result because I applied direct substitutions into the function here for x is equal to x and y is equal to 0. And the result is going to be equal to 1 because the limit is equal to 1, which is the same result as the limit along path x equal to 0. So you're moving on to finding the limit along the path y equal to x. So you want to find the limit along path y equal to x. So the limit of the functions as the point x comma y approaches x comma x. So you get x squared minus x squared over x squared plus x squared altogether square, and the result is going to be equal to 0. So since the limit along path y equal to x is different from those along x equal to 0 and y equal to 0, the limit does not exist. So since the limit along the path y equal to x is different from those along x equal to 0 and y equal to 0, we conclude that the limit does not exist. And that's how you determine if the limit of a function exists or not. So the common denominator between these two examples is that the limiting point of considerations, it does not belong in the domain of the functions. As you can see in example 4 and example 5, that when you find the limit of the function as xy approaches the point 0, 0, in the case of example 4 and example 5, which is the origin, so the point 0, 0 does not belong to the domain of the function. When you use direct substitution, it gives you an indeterminate form of 0 over 0. When that is the case, you may want to consider the two-path test for non-existent of limits. when you are asked this type of questions, most of the time, the limit does not exist. There are some cases the limit exists. However, we will have to take into account the precise definitions of limit of function of two variables, and this requires a lot of work to arrive at the answer. So now let me move on to another concept, which is continuity of function of two variables. In single variable calculus, you consider the function y equal to f of x, and you want to know what are the conditions that is necessary for the function to be continuous at the point x equal to a. So there are three conditions that you need to show in order to conclude that the function is continuous at the point x equal to a. That is, f of a exists. In other words, 8 is in the domain of f. The second condition is that the limit of the function exists at x approaches a, that is, the left-hand limit equal to the right-hand limit equal to the same value. And then the last condition is that the evaluation of the limit as x approaches a equal to the output of the function at x equal to a. Those are the three conditions necessary for the function to be continuous at x equal to a. Now in 3D space, when you consider the function of two variables, you have that the function f of x comma y is continuous at the point a comma b, is in the domain if the following three conditions are satisfied. As you can see, it's very similar to what we just talked about for the function of single variable. So that is f of a b exists, and so that is the point a b is in the domain of the function. The limit of the function as x comma y approaches the point a b exists. That is, you can calculate the limit of the function. And then the calculations of the limit of the function as x comma y approaches a b is equal to the output of the function at the point a comma b. Now we're going to do the quick calculations to show that the function of the form 3x plus 2y over x plus y plus 1 is continuous at 5, negative 3. So we need to show that the three conditions listed here are satisfied. So first, let's calculate the output of the function at point 5, negative 3. So that is f of 5, negative 3 equal to 3 times 5 plus 2 times negative 3 over 5 minus 3 plus 1, and this is equal to 3 if we do the calculations correctly. So the output exists, so the first condition is satisfied. Now, when you do the limit of the functions 3x plus 2y over x plus y plus 1 as the point x comma y approaches the point 5 negative 3, you can use direct substitutions, and by direct substitutions the limit is also equal to 3. So it's equal to 3 by direct substitutions. And for the last condition is that the limit calculation is equal to the output of the functions at the point 5, negative 3. So that is the limit of the function f of x comma y as x comma y approaches 5, negative 3 is equal to f of 5, negative 3. And that is equal to 3. So the three conditions are satisfied, so therefore you can conclude that the functions f of xy equal to 3x plus 2y over x plus y plus 1 is continuous at the point 5, negative 3. Sin the three conditions of continuity are satisfied, the function f of x comma y equal to 3x plus 2y over x plus y plus 1 is continuous at 5, negative 3. Okay, now let's move on to the last example. So in this example, we want to show that the functions f of xy, can you fix this for me please? So f of xy is equal to 3xy squared over x squared plus y to the fourth if x comma y is different from the origins, and is equal to 0 if x comma y is equal to the origin. This function is not continuous at the origin. So as you can see, the function is the piecewise defined function. The function is equal to the rational function 3xy squared over x squared plus y to the fourth if x comma y is different from the origins. So the function is continuous at all points of its domain, which consists of all points in R2 except the origin. So in order to show that the function is not continuous at the origins, we just need to show that one of the three conditions of continuity fails to be satisfied. So for the first conditions, f of 0, 0 is equal to 0, so that one is satisfied. Now for the second conditions, you need to show that the limit of the function as x, y approaches 0, 0 exists and is equal to f of 0, 0 along all paths that approach 0, 0. So for the first conditions, f of 0, 0 is equal to 0. Now for the second conditions, so to determine whether f of x, y is continuous, at 0, 0, we must show that the limit of the function 3xy squared over x squared plus y to the fourth as x, y approaches the origin 0, 0 exists and equal to f of 0, 0 equal to 0 along all paths that approach 0, 0. Very similar to example 4 and example 5, you can see that you need to find the limit of the function along the path x equal to 0, find the limit of the function along the path y equal to 0, find the limit along the path y equal to x. Now, if you use the same procedure as you see in example 4 and example 5, you may not draw any conclusions from those calculations. So you may want to calculate the limit of the function at a different approach. That is, you want to calculate the limit along the path x equal to m times y squared, where m is a non-zero constant. And when that is the case, and when you consider this path, the limit behaves differently. So consider the limit along the path x equal to m times y squared for m is a non-zero constant. So that is, you want to calculate the limit of 3xy squared over x squared plus y to the fourth as x, y approaches my squared, y. So x is equal to m times y squared in this case. So you get 3 times my squared times y squared over my squared altogether squared plus y to the fourth. And you get 3m y to the fourth over m squared times y to the fourth plus y to the fourth. That is 3m y to the fourth, and in the denominator, you can see that y to the fourth is a common factor, so you get y to the fourth times m squared plus 1. And if you cancel out y to the fourth, you get that 3m divided by m squared plus 1, for m is a non-zero constant. So when you arrive at this answer, you may wonder what can we do with this to show that the limit does not exist. So if you consider the value of m equal to 1, and remember the limit of the function exists along all the paths that approach 0, 0. So this is one of the paths, right? For m is a non-zero constant. So when m is equal to 1, you have the limit is 3 times 1 divided by 1 squared plus 1, or this is 3/2. Now for another path, when m is equal to -1, you have the limit is 3 times -1 divided by -1 squared plus 1, or this is -3/2. So you calculate the limit along two different paths and you have two different answers. From here, you can conclude that the limit does not exist. So since the limit does not exist as x, y approaches the origins, you can conclude that the function is not continuous at the point 0, 0 or at the origins. So that's it for me. Please let me know if you have any questions. Thank you.